Okay. Is Shikai being able to connect? And ping him. Yeah, I think before Shikai is figuring out his network problem, let's introduce two new members in our group. One is Chen Zhi from Taiwan, and there is the other is Leopold Marx from I don't from. It's he was our undergrad student, right? Now welcome back.
Thank you.
I would like to have everyone briefly introduce yourself. Get to know each other. Probably we can start from left to right. Yeah. Yeah. My name is Shandian Zhe. I'm a faculty member at School of Computing doing machine learning research. You all know that. So next, I think maybe Chen Zhi, you can introduce yourself. You're muted.
Okay. So my name is Chen Zhi Li. I'm from Taiwan, and I'm a first-year PhD student in Utah. And I'm interested in probabilistic machine learning, so I rotate in this lab. So nice to meet you, everyone.
Okay, next. And next is Da.
So hello, my name is Da, and I'm second year PhD student. I joined Dr. Zhe's lab last year, and currently I'm working on physics-informed stuff, like physics-informed Gaussian process and physics-informed neural nets. So if you have the same interest as mine, you can reach out to me, and maybe we can work on the same project. Thank you.
Okay, thanks. Leopold.
Hi, I'm Leopold. I'm from Louisiana. I went to Utah for a year in 2018. So I'm glad to be back. And I'll probably be working with Dr. Zhe and Dr. Pu from Atmospheric Sciences, and ideally maybe contributing to atmospheric modeling.
Okay. Shibo.
Hi, my name is Shibo Li, and I'm a fourth-year PhD student. And my research is about multi-data modeling and their applications to Bayesian optimization and active learnings. Thanks.
Zhimeng.
Hi, I'm Zhimeng Pan. I'm currently fifth year PhD student. My research area is mainly focused on temporal point process and tensor decomposition. I'm currently working on my final dissertation, and I'll be joining Pinterest as applied scientist. No, machine learning engineer. Maybe 2 months later.
Yeah, we hope to celebrate your defense very soon. Okay, next will be Madison.
Hi, I'm Madison. I'm co-advised by Dr. Zhe and Dr. Kirby, and I also work on physics-informed machine learning.
Yeah. Welcome. And I think Xin.
Hi, I'm Xin Yu. So actually, I have been in Utah for many years because I transferred.
Not that many.
Yeah, I transferred from another professor who has left for Google Research. So I started to work with Professor Zhe from last year. And previously, I worked on the computer vision, and currently I'm working on the neural network compression. And also, I started to work on some project, the AI for science. Yeah, thank you.
Okay, now Shikai. today's presenter. Yeah, would
Hi
you
everyone.
first introduce yourself and then start the talk?
Yeah, sure. My name is Shikai Fang, and actually I'm also the fourth year PhD student. And my research focus on the Bayesian tensor decomposition. I'm also interested to merge some physical knowledge like the SDE, PDE in the Bayesian framework.
Okay. Yeah, thanks for introducing yourself. So you can see that our group is growing. I would like to have like a very interactive, very active research environment. So you guys can discuss offline, and not only in the project, but also in, all kinds of stuffs, living in Salt Lake City, entertainment, and whatever. Right? So feel free to reach out to others and ask questions and sharing the information, experience, those things. Currently, I think a few ones. I think John hasn't been. John is in a job interview, so he cannot come, and he's not in the campus right now. So and because of the construction in the map, we don't have a large allocation of this common space using our group. But I would encourage you to, have some kind of union or activities together during the weekends or during the break, and get to know each other for fun, other than, out of the project. Okay, I think Shikai, today you're gonna introduce a new topic, right? So please share your slides and start your talk.
Can everyone see my screen right now?
Yes.
Yes.
Yeah, great. So today's topic is called From the Diffusion Model to the Schrodinger Bridge. It's not our research focus, because it's more like the generative models. But I think many of you can get some inspiration from the very topic diffusion model, and the very dense mass Schrodinger bridge is an interesting topic, and I think will help to broaden our view about the research of the machine learning. So let's get started. So here's the main contents about researchers. I will start from some very hot and topic diffusion model called the diffusion denoising model, and then introduce some framework called the score matching and lateral dynamics. And then we go to the world of the SDE and build the Schrodinger bridge. And at last, I will show you some application, which is kind of related to our research fields, how to use these things to build the supervised learning. So let's get started. So you can feel free to interrupt me if you have any questions. So here we just give a very quick overview about the mainstream generative models. I suppose most of you have the background or have knowledge about what is generative models. So unlike the supervised model, generative models is aimed to learn the distribution of the data. So actually, there are some lots of the mainstream generative model is here, the GAN, the generative adversary network, the VAE, the variational autoencoder, and the flow-based model. Actually, I have introduced like their normalizing flow or something, how they just build or generate or model their data distribution. The mechanism are similar. We first training something, training their transformation about something, and after the training, when we get a well-trained models, we just sample some noise from some Gaussian, denote as the red C here. Here are all the Gaussian distribution, the normal distribution, and then we feed this Gaussian noise in the well-trained the transition models or transition mapping, and then we want to use this combination to model the distribution about the initial data. So that's the high-level ideal and the mechanism about the mainstream generative models. So any question here? Yeah, great. So we'll go to the step. So keep the mechanism about the mainstream generative model in your mind, and then we first come to give you a very brief introduction about the diffusion. So diffusion is a terminology from the physics. So it's just describe the process which, like illustrated in this figure, you put some maybe inks or some things in the water, and during the duration of the time, the inks or the small particles will just diffuse into everywhere in the water. These things is called diffusion in the physics. And how we describe the final things, the final distribution about after long-term diffusion, actually is a Gaussian distribution. So here is the diffusion, how the diffusion is definition from the physics. And then we come to the problem. Can we somehow to reverse this process? This
Yeah,
means,
why it is determined by Gaussian distribution?
actually, because I think if you just there's a definition called the entropy. If you want to maximize the entropy with the infinite, the variance, the Gaussian distribution, the normal distribution will be the distribution describe these states. So the diffusion process actually is the entropy increasing process. So with the infinite step up about the entropy increase, the final distribution will be a Gaussian. I think that's the first principle of the physics, about statistical physics.
I'm not sure if you're yeah, because when you put this Gaussian distribution here, I thought you were talking about, for example, if those ink molecules fall in some Brownian motion,
yeah,
they're independent Gaussian. But you're saying when they arrive at a stationary state, the position of those molecules follow a joint Gaussian distribution. It is what you're saying.
I think in the physics you cannot say I can say that each directions or each location of the particles follow a joint distribution, but the whole system, I mean the whole system is energy or something, is follow a Gaussian distribution. Gaussian distribution is, I think it's not it cannot discretize or precisely to describe each location of the particles after long-term diffusion. But I think the whole state, it's a global state about this system.
But
You
the
can
state itself
describe
is determined by the location, also velocity, acceleration, those kind of stuff, right?
Yeah, somehow, yeah. But sorry, I because this is something about the physics. I'm not sure this how exactly the Gaussian distribution model the each locations about the particles. Here just a high level idea about how it happens.
Yeah, there is some conclusion in the statistics that for some continuous distribution with the same mean and variance, Gaussian distribution gives the maximum entropy. There is some conclusion on that, but I don't know how it's associated with this because when in the statistical physics, people use so-called Gibbs energy to describe the status of the molecules. That basically you just need to define the potential function over the state of these molecules. It can include the positions, velocity, even accelerations. Yeah, but anyway, go on. You can continue.
Yeah, and a very straightforward idea is given, because diffusion just describes the state from some given initial state to a final Gaussian distribution or very deconcentrated states. And can we reverse it? It means can we just from a random state from some Gaussian to the initial states of the data? If we could, and how we properly model this forward and backward things. I just here is not very, very concrete or very precisely description or definition. I just want to give you a big, the big idea about how the generative model we just talked about our first stage is inspired by the diffusion process and give you a new fashion or new style about the or new design about generative process. Here you can see something like the distribution about your data, about initial data. And finally, after some diffusion, you get a Gaussian noise. And given the Gaussian noise, we want to rebuild. We want to go back to the inner state of the Gaussian. Here I think is just a high-level inspirations about diffusion process in the physics. And then we come to the formal definition about diffusion models for the generative task. So actually, it's just model the random variables transition from your data distribution to a Gaussian noise with a bi-dictionary Markov chain. So in the forward process, we gradually add the noise about your initial data. And for the backward, in the reverse, we just given the Gaussian noise and we just do the denoising at each step. And we start from the Gaussian noise, and finally we'll gather some sample in the initial data distribution. So here is the big picture about the diffusion model for the generative task. So then any questions here?
So this is a framework of this Schrödinger stuff, your Schrödinger bridge you're going to discuss, or just for some general framework?
Yeah, here's the general framework for the diffusion models. Actually, the Schrödinger bridge, I will talk later, actually give a different model about this backward and forward transition, but not from the Markov chain, but from some SDE or something. We'll cover it later.
Okay.
Yeah, sure. And how I have a quick question. Is this diffusion process even reversible? From physics, I remember there's something or some law saying that this process is not reversible, because if you evolve from some initial state to later, then there's no way you can track down from the initial one.
Yeah, that's a good question. Actually, I think in the physics, the increasing of the entropy, from your data to a noise, this process, of course, is not irreversible. But I think in the model setting, in the machine learning, we can set it to be learnable, to be reversible. And I will show the details in the next slides. Okay. And we go to the model details, how we exactly build this forward and backward by the probabilistic framework. So first, we focus on the forward, from some data, x0, some image data distribution, and we in the forward process, actually, I think is for at each step about the Markov chain, we add in the noise with these transition kernels. Actually, here the xt-1 is the last stage about your transition, and here's the next step. Okay, it's just a simple Gaussian. The mean is just weighted. Actually, it's a small decayed state of your last stage, and then I just add a small noise on the previous stage. So here is the forward transition, the kernel for the forward Markov chain. And then with this transition, we can just write down the joint probability about the whole model. This model should be something like this one. Actually, if we want to build a transition of the joint distribution, we just add the qx0. And I think here is the joint distribution. Joint is equal to the initial distribution of our data, and you multiply this transition series of a transition kernel, and here's the joint distribution. And then we got a joint model to describe the forward process about from the x0 to the xt. T is the length of your Markov chain. And a very natural question is why you want to design the transition kernel, the forward one, by this term. what's the meaning about this beta t, about this square 1f beta like this. So the motivation or the reason we just designed the forward the adding noise process like this, because we have to ensure this process, the forward process, have to meet these requirements. This means when the t trends to be infinite, I mean the Markov trend is going to be stationary. The final transition of the final distribution xt should be your normal distribution. Here is the things we have to ensure, and here is things consistent with the diffusion, physical diffusion, the terminology. So I will give a very detailed
Beta t, the
explanation.
choice of beta t is constant or invariant along with t.
Yeah,
That's all.
actually, it's a good question. You can, if the beta t, you can set it as a constant, or you can set it as something variable or something. But if the beta t meets these requirements, the beta t is following the 0 to 1, it will meet its
And then
requirements.
you can show that when t goes to infinity, xt converges to the standard normal.
Yeah, I will show in the next slides.
Okay.
I have a question. So what is the p theta xt minus 1 given xt? What's the difference between the p theta xt minus 1 given xt and the q xt minus 1 given xt?
Are you talking about this term?
Yeah, the p theta and the q xt minus 1.
Actually, the p theta one here is something the backward things. We'll cover it later. Right now, we just focus on the forward process. We just focus on from the x0 to xt. So I will cover this term and this term later. Yeah.
Okay.
So cool. Yeah. Cool. Yeah. And how we just then we go to why the design about the forward adding noise process with this beta t. We can ensure these requirements to be met. Here I just give a detailed derivation about this one. So let your beta t just give some new notation here. As your alpha t became minus beta t. Record alpha t is still following the 0 to 1 range. And the USC, you can see for each xt, you can iteratively write down this definition by reparameterize, by just remove the noise terms over here. So like the xt is equal to the xt minus 1 add some noise. And we can further decompose this xt minus 1 this term to the previous stage to the formal to the previous last stage of xt and add one noise here. And here just the duration from here to here is just the probability about the merge of two Gaussians. And finally, we'll gather a closed for about the xt and its noise. And here is the closed for about given the x0 and after the t step about this adding noise, the final distribution will be something like this one. And just look at this one and consider when t equals to the infinite, the alpha t is defined right here. Because we record the alpha t itself is also in the 0 to 1, and the production about the infinite number ranging smaller than 1. So these terms will come to 0, and these terms will come to 0. So that show the requirements or show how the design about this forward transition can meet those requirements when t equal to trends to the infinite, and we'll gather standard normal distribution. So any question here? Yeah, great. So actually, I think this kindly answers the Shanian's questions. How we design the beta t, how we design is something could be hyperparameters to human design or be some learnable things. I think anything is okay, as it meet the requirements is fall in the range of 0 to 1. However, in the real experiments for the simplicity, people just set their use the use the linear things or use just setability like this one. Maybe set the max of the beta t like 0.9 and the smaller of the beta t maybe 0.01, and the middle beta t, I mean, is the scale of the noise we want to add. Just use the linear intersection about your min setting and max setting, and this human design. I actually in some paper, some authors just try to learn the beta t, optimal beta t, and they find it doesn't make any matter. So human design with this term or some learnable things to get a very similar process, similar performance for the generative task. So it's all clear here.
Okay.
Yeah, great. And then when we just building forward process, I mean the green one right here, like this one with these settings, and then we come to the Schwartz questions. Sorry, the adding noise should be here. Here's the forward. So and then we go to we focus on backward from the noise to the data. How should we design the transition kernel or transition formulas? So just like saying, when given the forward process, given sounds like this one, we can know how to write down the transition, to write down the joint probability about the whole model. So the p x0 to t, of course, we can write down as like the qx ln, qx0, and multiply these terms. So here's the joint probabilities. And with these joint probabilities, if I want to get an analytic for about the forward transition, I mean these terms. Of course, we can write down, use the Bayesian formulas to write down the formulas about the analytic backward transition kernel. And if you try it, you will find the analytic for the backward transition is totally intractable, because when write down Bayesian for, we'll see the formulas for analytic backward is revolving to the initial distribution about this data. These things is we never know. We only know the sample about the initial data distribution. So we can never know or get the analytic for about this optimal backward transition. So it's something just like lots of the fashion in their approximate Bayesian framework. If something from the Bayesian form is intractable, we just build parameterized models to approximate the analytic backward transition. And that's kind of answers both questions. We come to these terms. We use parameterized things to model, to approximate the analytic, the optimal backward transition based on the given for about the forward transition. So any questions here?
So P theta here is a Gaussian probability. It's a Gaussian.
Yeah.
Okay.
Yeah. I will show you the forms in the next slide how exactly this looks like.
Okay.
There's one problem. So if you do the Bayesian formula, if you rewrite the joint probability in the formula of P of xt times P of x big T, or P of x big T minus 1 given xt and so on, it probably doesn't satisfy the chain structure, right?
Didn't what?
Didn't satisfy the chain structure, like because if you decompose a joint probability, it's like P of x big T, P of x big T minus 1 given xt, P of big xt minus 2 given x big T minus 1, and xt minus and xt. Right? You're conditioning on all the previous variables.
Yeah.
So in your in the forward modeling, so they still just use this Markov structure.
Yep.
Okay.
Forward is Markov structure, and backward, if you want to write these things, you still just follow some Markov structure. So you have to just like you're saying, this is somehow depending on the forward Markov structure, and I think it's very hard to write down the formulas.
Okay.
And how we exactly design the form about this approximate the backward transition. Here comes these things. We just model the backward, I mean, from the 0 to t, from with a distribution like this one, still follow the Markov structure, just like the previous saying. We start from some pxt, here just some Gaussian noise right here. And then for each term, it's still a Markov trend like the transition. And the transition kernel what this looks like. We just model like the Gaussian, like Shibor says, and this mean and the variance. It's something like the parameterized and could be learnable to best fitting the joint things. So I have a question here. Yeah, great.
What is the in the mu theta and sigma theta? Why is there a t in the parameter?
Because these things is depend on the different Markov stage. So it's a function about t, right?
It's a non-stationary Markov chain. Consider the particular time step.
Actually, I want to put some actual comments here. Why we designed the backward like a Gaussian, a backward transition like with a Gaussian form, because when your t, I think, trends to infinite, so each forward is just adding a small noise. So the difference about between your different stage could be very close. So I think it's reasonable to just model it with a simple Gaussian distribution.
Yeah, I mean, if it's Markovian, then the process won't know which step is in because it's Markovian.
That's homogeneous Markovian. You can define inhomogeneous Markov chain. This transition that means the transition kernel is depending on the current time.
Okay.
Yeah, and then for here we have the forward, the given forward transition, and we got backward denoising distribution with parameters can be learned. The next step is how we just construct our object functions to learn the optimal.
So what is the px big T here?
What is what?
The p probability of the x big T first term.
Oh, this term.
Yeah.
This should be the Gaussian.
Isentropic Gaussian.
Yeah. 0 mean, okay.
Yeah. So this process is, I call it denoising because we start from some Gaussian from the x big T, and we serious about the transition, and finally we got the we should get a data distribution. There's a big idea. There's a story about this.
Oh, it's a constant.
You can call it a constant. Yeah. Okay, then we come to the next step. How to just build the object function to learn these things, or to let the forward and backward this two direction process to get as close as possible to reconstruct the whole story. Actually, the idea here is very trivial. It just use very classical the carrier divergence at the elbow things. So here, look at this function here. Here's just the carrier divergence about your qx0. I mean, qx0 is your data distribution, and the p theta x0 is your distribution, the approximate data distribution from the backward process. So actually, these terms is equal to these things. So it just integrate to cancel all the transition states of the Markov chain, and we got a parameterized or approximate distribution about your initial data. and if we just follow the distribution or sorry, follow deviation about the carrier divergence, and we want to minimize and use some trick and some deviation here. And finally, we'll gather evidence lower bounds like this one. I just skip the details about the variation. It's just some trivial things we have seen a lot of in the variational inference. And finally, the elbow for optimize these terms will come to these three terms. The first terms is just at the very beginning from your x0, I mean the data distribution, to the first step jump in the backward. And these terms you see, it just goes through for each distribution, each step of your Markov chain, the forward and backward. And this term is something constant because it's just based on I think this is Gaussian, and these things is just data distribution. So here's thing is constant. We just skip these things and focus on these terms. And the crucial term is these red ones. You see, this term is a carrier divergence about your here's your transition. It's your forward transition, and this term is the backward transition. So we want to minimize the carrier divergence at each step.
One question, Shikai.
Yeah.
So first, you said your L in the first line, in the top line is a carrier divergence, but this is not a carrier divergence.
Yeah, that's my question. So I thought the expectation should take the parametric family, not the. So what's the Qx0 is? Is the diffusion process?
Yeah, I mean the definition about this. Oh, sorry, that's my fault. I think it's not a carrier divergence, but it's something like the carrier divergence. I think so.
It misses an entropy term. If you want to do divergence,
it's an entropy. Yeah.
But the missing entropy is the
expectation of Q of 0 log ratio between P of theta x0 and log ratio of Q x0 over P of theta x0. So first, why this is a reasonable objective? You need to explain why you can throw out the entropy term.
Yeah, I think the starting point is just to the carrier divergence between Q and P, but the missing entropy term is simply the entropy of Q, but you don't have control over the data distribution Q, so you can simply ignore it.
Is this right, Shikai?
Yeah, I think so, because the carrier divergence is something like the Q, I think log PQ, right? Something like this one. And of course, if you just extend these things, you will get something like the because the log Q right here, and just something like the constants.
So you're assuming Q of x0 is some constant unknown distribution. This is what you assume.
Yeah, because the Q is given. Q is just the Gaussian drive at each state. All these parameters given. So we just focus on these terms.
Qx0 is given by the data, right?
Yeah, it's given by data.
X0. Oh, I forgot. X0 is the noise, or is the original data? Is the original data,
No,
right?
X0 is data. Here's data. And XT is the noise.
It should be Q over P, not P over Q. And L here is just a lower bound of KL divergence.
Oh, yeah, you're right. Yeah, I forgot the minus Q.
Okay, so you want to parameterize the forward models. That is
The backward model.
The backward model, and but from a Q, I mean the transition probability of Q is also like fixed. Like you don't need to estimate any parameters.
Yeah.
Okay. Okay. In a forward, that means in a forward procedure, meaning that you can make the data more and more noisy, right?
Yeah.
And okay, so you are marrying the similarity between the original data distribution and after you recover from noise, what is the distribution?
Yeah. So here, carrier variance is the target, the real data distribution, and the distribution recovered from some noise from the backward process.
And then why the IoT should be discarded in the bottom line?
You mean this one?
Yeah, this one you put a big cross there.
Yeah. First, these terms, the Q given x0 of the xt, that's just saying is a forward process. So the forward process is everything is there are no parameters to learn, so it's a constant. So this terms is about the xt, the pxt. xt as we learned, the optimal for just a Gaussian distribution.
Oh, so they both. So we can assume the p theta x big T is also constant distribution.
Yeah, it's a Gaussian. That will reach another interesting questions we're covering their scores. The optimal, the ideal case, the p theta xt should be a Gaussian distribution, but actually sometimes if the t itself is not set large enough, it will not cover to the Gaussian distribution. They will result in some other problems we'll talk later. But right now you can just think it's just a Gaussian distribution. Here's the ideal case.
Is it because both of them are Gaussian, or simply because p theta xt doesn't have parameters?
I think it's because he is just a Gaussian distribution. This term is a constant. It's nothing related to the parameters we are interested in. Yeah, so I have a question here. We'll go to the details about these terms. Yeah, cool. We'll go to the next slide. If you just check detail about the two terms right here, this terms, as I'm saying, we already give a parameter Gaussian form with a learnable mean and variance. And how about this form? This form is not trivial because in the problem setting in the forward process, we only give these things, we're given the Gaussian join of this form, but never give things. What happens when we're conditional on the x0? So to get the formal formula about these terms, the conditional forward transition, we have to use the Bayesian rule right here. So here's the Bayesian formula and the formulation about this conditional forward transition. And if you check each term on these Bayesian terms, these terms we call our Markov structures. This xt should only depend on the x per stage, but nothing related to the x0. The x0 here should be cancelled, and these terms, as we just like how we introduced in these slides. You see here, we have a closed form from the given the initial data and to the distribution after several steps about your adding noise. So each term in the Bayesian form is a Gaussian, and if all the terms Gaussian, and of course we have the analytical form for these terms, so it's a new Gaussian. And we can rewrite the form of the new Gaussian about this term. So I call it the conditional forward transition with these things. And his variance, scale of the variance is a constant, just decided by the beta t and alpha t. It's just a hyperparameter we set. And this mean is a function about your xt and x0. So that's the the detailed explanation about these terms. It's very important. And question here. Yeah, cool. Then we got another interesting facts right here. If you focus on this term, record. This term is just a Gaussian we just work out. And the green terms, the backward transition term, is still a Gaussian we set here. And of course, you know the Carrier divergence about two Gaussian distribution has the analytic form. So the elbow, so I just write down the analytic form for the given two Gaussian. There will be something like this one. And this will be the object functions we want to minimize and to optimize to learn the optimal, the mean and variance. So question here.
Could you go back to the previous slide?
Sure.
The mu t in the lower right corner, the mu to the t x0 xc is parameterized by the sum of two terms, but I think xt is the sample. Why can you sum these two samples here, xt and x0? It should be some parameter or some mean or variance.
No, record these things. Something like I call it the transition, forward transition, because the conditional is conditional on the current xt and x0. So he's a function about xt and x0. So his final form should be his mean. The formula about this mean should be a function about xt and x0.
Okay. It's a conditional k. Conditional k.
Yeah.
So xt and x0 are data, right?
Yeah, x0 is the data for the sample you draw from your initial data, and xt is something just use the adding noise, the analytic form.
Meaning that you actually have already generated x0, x1, x2 on Q big T, right?
Yeah.
Okay, so this L is only for a single sample from data?
Yeah, you're right. So actually, I think right here is let me organize my words. It's not on the single data, because you finally will take expectation over all the samples you draw from your x0, I mean from your initial data distribution.
Well, I think when you apply this model, it's like, okay, I got like 100 or 1,000 images, right? For each image,
yeah,
one instance of x0, and then you apply this forward procedure first to arrive a series of noisy images until like total white noise, and then you just construct this elbow across all those noisy image sequences, right?
Yes.
Okay. I have a question. Why don't you switch the Q and the P in objective?
Switch Q and P.
Yeah, like here there's a notation here is a little bit confusing, because when we want to estimate something, we usually use Q rather than P. But here you assume Q is kind of constant knowing thing, and P is something you want to estimate.
Yeah. But I think these things just confused me at first. But I think in the diffusion model community, everyone just follow these things.
Yeah, and the problem is that, okay, why? Because you want to estimate the KL divergence. Why not you switch the KL terms? Like this is KL between Q and P. Why not it's P and Q, right? It's like variation inference, right? Our approximate distribution. We want to minimize the KL divergence between the approximation and from the approximation to the true posterior, right? So now you're trying to minimize the distribution from the true to the approximation.
That's a good question. I never think about it. I think maybe for the final durations, it's not such elegant like this. I don't know.
Yeah, and one thing is you can save some work by by setting the KR in this way, because first you will save the entropy term. Otherwise, if you switch the KL position, then you need to include the entropy term, which will be a little bit of trouble.
Yeah, that's that makes sense. Okay.
Yeah, I think maybe another reason is if you change the P and Q right here, the final 4 you got is expectation over the P. It's not Q, it's expectation over the P. However, it's the expectation over the P is some distribution you want to learn. You cannot sample from the P.
Oh, I'm not saying it's not sample, but it's you need to use some reparameterization trick.
Yeah.
Okay. Yeah.
Yeah. And here is our final abstract functions. And of course, we can further to simplify it. So how we exactly do this to do the first thing we find. So first, we don't learn the variance about their approximate backward position. We just set it as a constant. I think people just set it like the beta t or beta half t, which is exactly same with the forward process. So the forward and backward, the two joint, they have the same scale of the noise. So it's kind of make them as close as possible. And another very interesting thing is we just rewrite the formulas about this lambda t, and we'll find lambda t has some form like this one, because based on the current xt and Gaussian noise, if the lambda t, is the tutor lambda t actually record is the mean of your forward transition. If we want to make the backward transition as close, these two terms as close as possible, how about we just set the backward transition has the exactly same four about your transition mean, about your forward mean. So here we just set the backward mean with this 4. And we only put the parameter things, the learnable parameter models, to model this noise. And other things we just keep the same. And with these settings, these things are get very close. If that makes sense for you.
But isn't ZT the you don't know the ZT, right?
Yeah, I don't know. No, ZT is something like the Gaussian noise. It's just a Gaussian noise. We know the ZT.
But if you know the form of the conditional distribution qxt minus 1 given xt and x0, you know the mu theta, right? You know the mu theta. You just set it to mu theta.
Yeah.
Isn't that done? Like you don't do any learning.
We just learn these things to these terms. Yes, there's a term, I call it the time of varying data to noise mapping. So given here should be
which you learn ZT, right? But ZT, my question is that do you know ZT in the forward conditional distribution? You got a mu theta xt x0 with an analytical form, right?
Yeah, I know that. But this ZT is asking if the Gaussian standard Gaussian noise is based on the sample. So here we just set the mean about this with the same 4. So these things should be a mapping. Given the data, current data, given the t, it should be output some Gaussian noise or Gaussian normal distribution to exactly match the forward mean.
Oh, okay. So you got this data, you got ZT from the forward procedure. Now you want to map, you want to learn mapping from xt and t to this ZT.
Yeah. So I call it data to noise. Yeah.
Okay. All right.
Yeah. You somehow like the, I think like the VAE, you feed in the data, and after some network transition, you will get some, you want to get some Gaussian standard Gaussian distribution. It's just like the encoder about the VAE.
Okay, okay.
And we simplify, we just plug in this simple setting in the object function about such KL divergence. And here is the final, just the most simple verse to simplify the loss function. So its expectation using in the alter is on the t, different t, expectation on your x0, I mean the data sample you draw from your Bayesian distribution, and the different, the sigma t, I mean the Gaussian distribution. And the inner terms is just the RNC between the real Gaussian noise and your data to noise results based on the current things. This term is just the xt. So if that makes sense, here is no trick here. Just plug in the simplified setting in the object function, and you will get these terms. And the training and the sampling is quite trivial. In the training, we just first sample their data samples from the distribution, draw the t from all your market chain teams, and draw sample of some Gaussian noise, and just take gradients about this one, and to optimize your theta and until converge. And in the sampling, when you after training, I want to generate some image, generate some sample for initial data. I just from xt draw some Gaussian noise and just follow the backward. Here's the backward form about your backward transition at each terms, and finally we are gathered x0. Any question here?
So what is the form of z theta or the epsilon theta?
What's that? You mean this one?
Or z theta?
Z theta.
Yeah. Is it there's a functional form or is a neural network?
You mean this one?
Yes.
Yeah, it's just a Gaussian. And the sigma t, as I say, just we set it as the exactly same scale of the noise we put in the forward process.
Then in the algorithm 1, the step 5,
yeah,
then take gradient with respect to what?
To theta. Theta is the models, is the data to noise mapping models we want to optimize.
Yeah, that's what I'm asking. What is this model?
What is this model, you mean?
Yes.
Yeah, it depends on the format of your data. It could be some, if they're in match, they just define as like their UNet. If they're something like their NLP data or some any neural network based or any models, you can, the input is your data and output is the same size as noise. So any model, linear model, neural network or something, everything is good.
Okay.
And the epsilon here, the epsilon here is the same, right?
Yeah.
In line 4. Okay.
Yeah. So because it's expectation, you see, it's based on
you got one epsilon, you got sample epsilon as your ZT, the instance of ZT, and also to calculate xt, you involve the same epsilon as well. Oh, okay. Okay.
Yeah.
Then that makes sense. Otherwise, yeah, that makes sense because you're trying to map back after you transform epsilon, and then you want to map back to epsilon. So your model.
Yeah, so it's kind of surprised me when I first read the diffusion model because the model setting is kind of quite complex. But finally, with this simplified setting with derivation, the final loss function is very simple. And actually, what we're doing building a model to match the Gaussian noise. So at the first step of at the first go through this model is quite surprised how these things can be such simple. And but there's the magic, or that's the magic about this diffusion.
That's like a stacking of VAE, or you can say multi-layer VAE.
Yeah, you are right. These things look very similar to the VAE, especially to the VAE encoder, but they just use one or several layer of a neural network to do the data to noise mapping. However, right here they use multi-step or Markov trend to do the data to noise mapping.
Where do you apply this algorithm to sampling? Looks like this is you know X0, right? But why do you sample X0?
Yeah, X0, imagine there could be some, maybe the ImageNet could be some existing data point, right? And I want to generate it. The new sample also belongs to the X.
Oh, that's the generation procedure.
Yeah. That's generation. That's a generative model. We're trying to model these things based on samples.
Oh, okay. And then in the training procedure, okay. So you're sampling like if you sample T, you essentially simulate the noise the corrupting procedure to T steps, then you update model. Oh,
Yeah.
okay. We're doing this essentially integrating all possible corrupting steps to big step T.
Yeah.
Then you want to update the you want to estimate file. Okay.
Yeah. So and actually I think the diffusion model is proposed in 2015. So it's not a new thing. However, it's not after when it's proposed, I think 7 years ago, it just didn't get too much attention by the community until the DDPM paper. This paper has come through, I think, 2 years ago or 1 year ago. I can't remember, because the raw version about this diffusion model performance is bad. It cannot get a very good performance, especially for the high resolution generation. So people just say, yeah, I see this model is interesting, but it's useless. And DDPM, I mean, this paper just apply the very similar structures, but use lots of the tricks, like I'm saying, how to simplify how to simplify these things, how to set their distribution, how to set the form about the multi, instead of maybe you just use a big neural network to follow these things. It works, but actually it's hard to train. But if you simplify it with these forms, it's easy to train and easy to write their loss function. So that's the contribution about the DDPM. It's just to propose some very easy, some simplified trick. And finally, you get the state-of-the-art performance on the high resolution generations. And that's the reason it gets lots of attention, and people say, wow, the diffusion model can do such a good job. And I think lots of the big model, like from the DeepMind or something, they just use the diffusion model to do the generalization. That's their image generalization.
So those the algorithm details you told is all about DDPM.
Yeah.
So it's better than GAN.
Yeah, even better than GAN. They compare their performance, generative performance compared to GAN, compared to VAE. The diffusion model is the best. And DDPM is only our first step, because our final goal is the Schrodinger bridge. DDPM is a very short at the beginning. So I think maybe how many time I have for this presentation of our?
Yeah, you can continue. If you cannot finish at 12:30, we can come back at 1:30.
Yeah, sure.
It's 1:30, right?
Yeah, sure. And we come to the second step. I mean, another perspective about the diffusion model. I mean, this loss, because I think when I first lab about this loss, it looked very strange because we're trying to learn something to match the Gaussian noise. So actually, there are another perspective to work out the same formula, exactly the same formula.
Yeah. One comment.
Yeah.
Shikai, one note I want to make here.
Yeah.
Compare with again, this DDPM actually has more explicit procedure to generate or corrupt the original data, and another more explicit model structure to recover that. If you look at again, it's just doing some neural network transformation, right?
Yeah.
No matter you're corrupt the original data or you want to recover that. But if you specify a more simplified structure, it might be easier.
Yeah, I think so. Yeah.
Okay. Yeah. Please continue.
Yeah, sure. And we come to another perspective I want to introduce about diffusion model about its DDPF. It's called score matching method and large range dynamics. Actually, from the previous introduction about diffusion models, just rethink what we are doing. We just set the forward Markov transition and their approximate backward transition, and then build their loss function, and that's it. Use the variational inference or something. And here, the reason I want to introduce another perspective is we want to generalize this DDPM to like the continuous case to the Schrodinger bridge case. The score-based perspective about this diffusion is crucial. So I want to introduce right here about what is the score matching and what is this large range dynamics, and how the combination about these two can come to exactly the same results about these things. And you will have a deeper understanding. What is it this loss function is exactly doing? What is loss function exactly learning? So let's get started. So what is the score function? What is the score? So as we know, for a probabilistic model, we can always write down his perspective. Write down his PDF like this one. Here's something very similar to the energy-based function, and we can always set something like the very free attribute for about the function f theta. We don't have to apply any constraint about f theta. It could be a neural network, could be anything. His output scale could be anything. However, if we want to ensure out the probabilistic the PDF about some distribution is valid, we have to put this in this form. I mean, divided by your freedom, the free form, the function delivered by a constant, and then we can ensure this p theta xt is equal to 1. This means the distribution PDF we want to model is something that is valid. However, if you want to directly to model like the f theta with some neural network, and use the f theta to model their p theta, it's very hard. Why? Because if your neural network is trained very well, it's very hard to get what's the z theta, what is the constant, the normalizer, what's the floor about this. So that could be a big gap or big challenge for you want to parameterize or parameter distribution or PDF distribution. And what is score function? What is score-based method? So the score-based solution just provide another approach to parameterize the PDF or distribution. This means I don't parameterize the p theta or f theta itself. I parameterize its score functions. So what is score functions? Let's just see the red box. Just assume we have some distributions, and we have the PDF, and the gradient respect to the log probability about distribution. We call it the score functions. And we can train a model, a neural network, or any parameterized model to model the score function about this one. And we will find after some very simple derivation. The final things is no longer related to the constants. They're very they're intractable constants. So that would be a great thing. So we will count, and we can learn the score functions about this one. We can do the sample from the target distribution we want to think. And how we exactly do this, I will introduce in the next slide. Here, I just show you as we have the score function and we give a model to approximate this score. And there's a family about the method to call the score matching. This means I want to minimize the feature divergence about your score functions and you approximate the score. And that is. So we don't have too much details to go through how to exactly do the score matching, because if you regard this as neural network, these things you should be some your training data or training samples and how you exactly gather things from or unknown distribution. There's lots of the tricks. We will skip here. Just show you what is the score function and what is the target, what is the objective to gather a score function. There's a feature divergence. And then if given the score function, given the well-trained approximate score function, how we draw the sample from the p theta x. That comes to another very crucial concept in the machine learning sampling community. It's called the large range dynamics. It's just assume we already got the score function and how exactly, and given some initial, maybe the Gaussian noise, how exactly from the Gaussian noise to the target distribution. We just follow the rule like these forms. So just somehow like the, what are they called? The Hamilton dynamics or the Gibbs, not Gibbs sampling, it's a Monte Carlo samplings. It's just, we start from some Gaussian and in each step, we just follow the score function and follow this mechanism. And finally, when you jump in steps, this is trying to the infinite. And finally, the final xt you got, it will be your target distribution. So here, just give you a very high level introduction to what is a score function. It is. If we look this figure, the score function just like the gradient field, or you can call the vector field. And there is a black row right here in the figures. And here maybe our target distribution or mixture of Gaussian. And if we just randomly from here, we sample data from here. And how the data from here to the target proposed, we just follow the gradient field or the vector field to move step by step. If the length of your moving step is longer enough, you'll finally, no matter what's your start point, finally you'll get a very high density allocation about your target distribution. So that's a big idea about the large range dynamic and score-based function. So if you want to learn the gradient field or the vector field about your landscape and doing the large range dynamics, no matter where was your start point, follow this somehow like the gradient descent, follow the vector field, follow the gradient field, and finally you will get a high density field. So there's a high level pictures. So any question here?
So it is a Brownian motion with a vector field, right? With external forces.
You mean which form?
External forces.
Yeah. Yeah, I think Zhimong, because
Go ahead.
because I remember Zhimong has introduced something like large range dynamics years ago. I think he has more details about what exactly is doing. Yeah. And then Well, I think that's enough to at least for this project about score function and the large dynamics. Actually, there are lots of the extension like the scan gradient we have introduced briefly. It's also based on the score function or something. But today we are focused
But
on
if,
the connection. Yeah.
Yeah,
Go
sure.
ahead.
I think if you have the gradient of the logarithm of normalized
Yeah.
density, you can also construct an HMC Hamiltonian dynamics, right? If you augmented variables kind of like separate Gaussian. I think it's still doable.
Yeah, I'm not sure exactly the difference about Hamilton dynamics and the Lagrange dynamics.
Because they both are using gradient of the log normalized density to evolve the position into the, how should I see that? There should be some region with which you can high density region. Yeah, I think the Lagrange dynamics might just be easier to implement.
Yeah,
but it should be also it should be also to use like HMC. Just introduce an additional variable and follow like diagonal Gaussian. Just follow the same procedure. Just run the leapfrog. Right? There's another numerical integration.
Yeah. And what's the connection about this Lagrange dynamic transfer function to the diffusion model we introduced today? Actually, I want to show you there. Just the score-based model. You should follow the score-based model and Lagrange dynamics. You can just given like something like the forward transition from some data distribution from here's your data, here's your initial data distribution, to some noisy data, adding noise process, follow this Gaussian drive, follow this Gaussian trends, where these things is just consistent with the DDPM setting. And they will just write down the score matching functions or the score matching object functions. It will be something like this form. And we use the score matching and gather very well trained the score match or the score simulator network like this one, and then we use the Lagrange dynamics to sample from some initial data to the based on current score or current gradient to a next step. It's exactly match the form about DDPM. So DDPM right here. So actually, here's these things. It's just the gradient. Is the gradient about this thing. It's not exactly matched because I think these things, the gradient or the score about your forward transition, is something like the x hat multiply the epsilon t. And how we design the score matching right here, we design the score matching function, also like the maybe the theta x minus one will be the epsilon t. If you do these settings, record these things has a closed form because it's just a Gaussian, and his gradient about this term about log gradient is something like a closed form, and we want to design the S theta, the score approximator. We design this form, and we just plug in these two, and finally we'll get loss function about the DDPM. We just derive out in the last section. So here, just give your understanding. So what actually the loss function about the DDPM is doing? It's doing the score matching. It's trying to learn the gradient about your log probability at each step, and the forward, from some noise from your noise to your initial target data. They just follow the Lagrange dynamics. If you check the paper, it's exactly consistent. So we have another perspective about the diffusion model. Recall in the last section, we derive out the loss function, derive out the things, calculate the Markov trend. And by building the lower bounds about the variation lower bound or something. But here, from the score matching, from the score-based model and large range dynamics, we can exactly get the stem for all these things. So here's the idea about the score match and the connection with the diffusion model. So a question here.
So by following this score matching objective, you can recover the loss of DDPM?
Yes.
Oh, that's interesting.
Yeah.
But how do you, if you sample, so executor here should be some intermediate step, right?
Yes.
And then if you want to sample, if you want to generate sample from your score, it's your model. How many steps do you conduct this large band dynamics?
Yes, I think it's also human design. I think actually it depends on the big M. It's just like the big T in their diffusion models.
Yeah, but if you use big M steps, how can it arrive at the same loss of DDPM?
I don't get the point.
I mean, like if you want to minimize your score matching based objective, right? Every time you sample X tilde, this X tilde, of course, can be through some forward procedure. You simulate that through your P model. And then
sorry, it should be the big N, I think, because we want to score matching at each step about this transition.
At each step, so N is the number of examples, or N is number of time steps.
Number of the time step.
Okay, with number of time steps, then X tilde. Then what does X tilde mean? X tilde is the step I. After you craft the original data for I steps.
Yes.
And then
I think X tilde it should be here. I mean, it's better to note it as XI.
Yeah, XI is replaced by X tilde, right?
Yeah.
And then you got XIM, right? XIM should be sampled from this large band dynamics for a few steps. You're running for big M steps. You got XM. XM is actually a parameterized sample.
Yeah. So the large band dynamics actually is just equal to the backward transition about your diffusion. So for the backward diffusion, we as last section, we start from some marker trend, and we'll find the marker trend after exactly same for with the large band dynamics. So these things are exactly the same.
So the number of steps you arrive at I will be like a big T minus I, something like that.
Yeah. So actually here, I think here's maybe some confused. I think here should be the N, the small n and big N.
Yeah, that's some. There are some details missing here. The reason I'm asking this is because if you're using large band dynamics to simulate that, you need to it only guarantees you get the exact sample. You get sample following that target distribution after infinite number of steps, right? Even you have a given model.
Yeah, but in the diffusion model, it's granted to you from some data to a real normal distribution after the infinite step about your marker trend. You have to set the T in the diffusion model.
Yeah, of course you have to set a T, but this number of time steps is the same of the big T here. A kind of question because you have your backward model is still a Markov chain, right? Even this logarithm of normalize the joint probability of that, you can still like generate a lot of samples to move that samples of for many steps to ensure that your XIM really follows your backward model.
So I think I cannot sure, sorry. But I think the T and F and here should be the same things. Is the length of your dynamic sampling of the jump steps, or the length of your Markov trend division models. If you set them equal, I think these two models are consistent.
Okay. Yeah. Let's continue because the details are missing. We cannot figure out the reason. But anyway, we get the idea.
Yeah, sure. So here I just want to let you know the DDPM diffusion model and the score-based model and Lagrange dynamics. They are the same things actually with some settings. They are the same things. And the last function about your DDPM actually is just to learn the score or learn the gradient of your log probabilities and to recover from the noise or through some noise to your data to the forward and backward. Yeah, that's the big story.
Okay.
Yeah. Should we left the left section now too?
Yeah. I think we can because it's a lunchtime, right? So let's start on what's the time point I mentioned in that?
No, 2.
Those 2 is too late. Yeah.
The email I received says 1 p.m.
1 p.m.
It stated in the email.
Is it good for everyone to return at 1 p.m.?
Yeah, good for me.
I prefer
Yeah, it's fine.
1:30.
1:10.
1:10?
Yeah, 40 minutes.
Okay, yeah. Let's continue at 1. Oh, how about like 1:15? Yeah.
Okay.
Yeah. Let us return at 1:15. So let Shikai to finish the introduction of the remaining things. Okay.
Yeah, sure.
Yeah.
See you.